Hello. In this video, we are going to continue our discussion on shapes, and there are two types of shapes that I want to discuss here. The first one is called electron domain shape, and the second one is molecular geometry. And for a given molecule, you'll need to know how to determine both. Now, in the previous video, we looked at bond angles, right? That video was 07B20, and we looked at bond angles. And we also discussed a little bit about the names of these different types of shapes. I want to remind ourselves of one particular molecule, sulfur dioxide. And sulfur dioxide has a central atom sulfur, double bond O, and a lone pair. Fill in the rest of your lone pairs on your oxygens, and you'll realize that every atom is neutral. There is no formal charge. And we were talking about bond angles. And the thing is, I like to think of these electron pairs as balloons. And we're going to encapsulate a lone pair in a balloon, encapsulate a double bond as a balloon, and this double bond on the right as a balloon. And if you hold three balloons, 1, 2, 3, from the tips, then they will naturally form a trigonal planar shape. That, in our case, is called the electron domain shape. Let me write that down. And that's one of the shapes that we need to be concerned about, the electron domain shape, trigonal planar. And I have a model of it right here, okay? Even with the double bonds to the oxygen, which is in red. To separate those balloons as far apart from each other, that bond angle is approximately 120 degrees. So ideally, the ideal angle is 120 degrees, but that comes from the idea that this is trigonal planar. So trigonal planar molecules have bond angles that are 120 or close to 120. We saw some deviations, and because a lone pair repels bonds stronger than bonds repel each other, the two double bonds squeeze together a little bit tighter, and technically this is 119 degrees. But don't worry about the deviations for this video. Okay. Now, there's the model, and we're counting the lone pair as a balloon, the double bond as a balloon, and this double bond as a balloon as well. But the second type of shape that you have to be concerned about is called the molecular geometry. And the molecular geometry is only based on the atoms. Now the atoms are in that arrangement due to the balloons, but when we finally state the shape made by the atoms, you get rid of the lone pair from your model, okay, and we see that it's bent. It's not linear, okay, it's not 3 atoms in a row, it's bent. That is the shape, or what's called the molecular geometry. So think about what's needed for these pieces of information. The electron domain shape, and we're going to think of these as balloons. Okay, that gives you the electron domain shape, but it also gives you the angle. The molecular geometry, you're going to look at the atoms. Okay. Now, I have a study sheet that has all the shapes that you will need to know. Before we get to that, let me just remind you, well, actually, let's get to that. I was going to write down a list of what constitutes a balloon. We already seen 2 examples. A lone pair can be a balloon, a double bond can be a balloon, but also a single bond and a triple bond can be a balloon. Okay, so I promised that there's a study sheet that has all the shapes, the electron domains, and the molecular geometries that you will need to know for your class. Let me find that. It's a, oh, here, PDF. Okay, hopefully you can see that, and hopefully there's a cursor that you can see. But what were we just doing? We were doing sulfur dioxide, correct? Sulfur dioxide is right here. And yes, I'm looking at my notes, and we call the molecular geometry bent. That's made by the atoms. But the shape made by the balloons is actually right here, trigonal planar. So in the trigonal planar family, this is the electron domain shape. We have two members with different geometries. We have a trigonal planar geometry, and that molecule that represents that could be boron trichloride, and we have a bent. The strategy is, okay, let's look at tetrahedral, because we did look at tetrahedral in the previous video, and we started out with, I think, carbon tetrachloride. Here we have carbon tetrabromide. The strategy here is that all three of these molecules have four balloons. It's just that some of the balloons are bonds, and some of the balloons are lone pairs. And the idea is start with the first member, and then you pluck off an atom and describe the shape made by the atoms. Okay, but all the balloons are still there. All four balloons shown here. That's tetrahedral. Okay. Now what we're doing really is getting rid of balloons but maintaining the tetrahedral shape. All right. So the three members for the tetrahedral family are tetrahedral, trigonal pyramidal, and bent. You notice that, and we'll do some of these examples. I know we don't have Lewis structures drawn yet, but you notice that if the central atom has no lone pair, the electron domain shape and the molecular geometry are identical. So when you have a lone pair, that's when you have a different molecular geometry than the electron domain shape. So I've summarized a couple of those points here in the upper right corner. There are two types of shapes to consider: electron domain shape and molecular geometry. For electron domain, think balloons. For molecular geometry, think atoms. Here is a list of what constitutes a balloon: a single bond, a lone pair, a double bond, and a triple bond. Okay? It's just the electrons are fairly, close together in a triple bond that you could encapsulate all 6 electrons of a triple bond as one balloon. And it will act as one balloon or one electron domain. Keep in mind that all of this is still based on VSEPR, right? Valence shell electron pair repulsion. So in purple, this shape of the balloons is due to VSEPR theory. Okay, not a big deal. It's just, these terms are connected to each other. Okay, let me show you a couple examples where we have an expanded octet, or another way to say that is hypervalency of the central atom. Okay. And last thing is, in this box, we have bond angles, and those bond angles we talked about previously. We didn't talk about all the families in the previous video. Here we do show all the bond angles. Okay? And we'll get to this in just a bit. All right. I haven't talked yet a lot about the linear family. And it's 3 atoms all in a row, and an example of that is linear carbon dioxide, or just carbon dioxide. Why don't we do that first, and then I'll get to the harder ones. So the idea is, on an exam, maybe you're given a molecular formula, and you got to figure out the Lewis structure. Make sure if they ask for a Lewis structure, you show all the lone pairs. Understand that this carbon has two balloons. And when you hold two balloons from the tips, you're going to get a electron domain shape. We'll just abbreviate it EDS, equal linear. The central atom has no lone pairs. We would predict that the molecular geometry is bent. Oh, sorry, not bent, linear. We would predict that this bond angle is 180 degrees. Okay. And for now, that's all the information that I want to talk about. That's linear. Okay. Would you consider, I don't know, a diatomic ion or a diatomic element as linear? You would have to because, right, 2 points make a line. So technically, you would also think of this as linear. But really what we're looking at are examples that have a central atom, a distinct central atom. Okay. We've gone through the Trigonal Planar family in the previous video and a little bit here with the SO2. That bond angle is 120 degrees. In the previous video, we said that there could be deviations because a lone pair will push harder away from the bonds, thus pushing the bonds closer together. Okay. And don't worry about the cartoons. I know there's one line here, but you know now from our Lewis structure that this is a double bond. Okay, this is just a representation of the shape. For the tetrahedral family, again, this is the electron domain shape, and it's a shape made by the balloons. We have tetrahedral. If you pluck off an atom and replace it with a lone pair, you have trigonal pyramidal, looks like a pyramid. And then if you pluck off another bond and you replace it with a lone pair, now you can't have a pyramid, you have what's called a bent. Okay, and again, all the balloons are still shaped as tetrahedral. That's why we put these three molecular geometries in the tetrahedral family. There are two other families. Okay, the first one that we're going to look at is a trigonal bipyramidal family, and there are 1, 2, 3, 4, 5 balloons. And this arrangement that you see on the screen, that is the best way you can I do this full screen? It's a little bit smaller. Let me just do this. So for the trigonal bipyramidal family, that is the best way you could separate it. That is as far as the balloons can be from each other. But we have actually two angles here, two main angles. We have a 90-degree right angle, okay? And then the three atoms, the three outer atoms that are in the plane, they form basically a trigonal planar. So that's 120 degrees again, just like we had up here, 120 degrees. I don't know. It wasn't in the previous video. Oh, it was. We talked about wedges and dashes. So see, this atom is kind of coming towards us, and that's indicated by wedge. And here we have one going away from us, dash. So all 5 outer atoms are here. That's called trigonal bipyramidal because the central atom has no lone pair. It's the same as the electron domain shape. If we take off an atom, we get seesaw. Why do we take off this atom right here? Okay, because by taking off this atom here, we still maintain the trigonal bipyramidal shape made by the balloons, but also this still maximizes the, how do I say this? Still maximizes the distance between the bonds. It's actually better to remove this bond right here. Okay, that's 120 degrees away from these two bonds on the right, than to take away this bond right here on the top. Okay. Because let's see, let me just double check this. Well, it just maximizes the total distance between each of these bonds. Okay. Let me show you a model, and maybe that will help a little bit. The model for the trigonal bipyramidal looks like this. And see your three atoms, three outer atoms that are on the plane, horizontal plane. And then what are we plucking off? If we have to remove an atom and replace it with a lone pair, we would take off one of these three atoms in the same plane. Okay, so that's exactly what my drawing looks like. And we call this seesaw because if you tilt it like this, now you'll see a seesaw. Okay, it'll go back and forth, up and down like that. Okay, so that's seesaw. What is the next atom to remove before we go back to the picture? The next atom to remove is, which one would be the best one to remove? It would be another one of the ones that are in the same plane. So I'll remove this one. Okay, and we have this. This is called T-shaped. T-shaped. We have 90 degrees separating these. Okay. Let me just double check something. Yeah. Because here we have the three bonds like this. Now, where are those lone pairs? Because I still have to maintain that we have a trigonal bipyramidal shape made by the balloons. So we could replace the bonds with lone pairs, and we have this right there. Okay. And then the last bond to remove, so there are 4 members in this family actually, is the last one that was on the horizontal plane, and we have this. See, definitely now that makes sense because now the 2 bonds are as far apart as possible. It wouldn't have made sense, right, if I started out with this shape. Okay, this is called T-shaped. It wouldn't make sense to remove this bond down here. Okay, because now these 2 bonds are 90 degrees to each other. Okay, it's better to have them 180 degrees from each other, like that. So that was kind of the point I was trying to make when we decided to remove that first bond. Okay. So here are your 4 members of the Trigonal Pyramidal family. And why don't we go ahead and try this one, BRF3. We call this T-shape, but let's prove it from the very beginning. BRF3. All halogens. Again, another strange one. BRF3. Okay, I'll go through this step by step. There are a bromine has 7 valence electrons. We have 3 fluorines that have 7 valence electrons each. That's 28 electrons that we have to account for. We have bromine in the middle. Again, when in doubt, it's the less electronegative atom that's the central atom. And I don't know what the shape of this, because I don't know off the top of my head how many lone pairs bromine will have, if any. So I'm going to draw this just like a, I don't know, just like it looks trigonal planar. But I don't know if it's trigonal planar because I don't know how many lone pairs bromine has. After you put single bonds for all of your outer atoms, make all the outer atoms satisfy the octet rule. So I added 3 lone pairs for each fluorine. That's a total of 24 electrons. I'm missing 4 electrons. That's 2 lone pairs, and go ahead and spread out the 2 pairs like that. Realize that you have 5 balloons. If you have 5 balloons, then your original shape was this, right? Five balloons. But we removed 2 atoms, right? 2 atoms, 1, 2. So the 2 atoms we removed were, let's take off this one and this one. So what do I have? I really have T-shaped. Okay. And what are the bond angles? the bond angles are 90 degrees. This one's 90 degrees as well. Okay. We lost the atoms that define 120 degrees. Okay, because there's no other atoms in the same plane as this F, like there were originally. Finally, this is called T-shaped. So in terms of the EDS, the electron domain shape, Trigonal Pyramidal. In terms of the electron geometry, no, not electron geometry, the molecular geometry, T-shaped. Now, are these angles perturbed? Are they deviating from 90? Actually, they are, because these lone pairs are pushing the bonds a little bit closer than they want to be. So let me put here a less than 90 degrees. Less than 90 degrees. Okay. For instance, here, let me make this T-shaped again. Right there, T-shaped. So, and then we could hold it like this, T-shaped. So it's these lone pairs that are kind of pushing against the bonds, and they're putting the bonds a little bit closer together, less than 90 degrees. So I'm trying to squeeze them together, okay, because of the repulsion between the lone pair and the single bond. For my class, it will be important to know whether it is very, very close to 90 degrees or is it less than 90 degrees. For my class, it will be very important for them to know whether this bond angle is very, very close to 120 degrees or less than 120 degrees. And in this case, it's less than. Okay. Whenever you have that lone pair, then yes, chances are it'll be less than, but you got to analyze it on a case-by-case basis. Okay. Because, for instance, over here, okay, so we just did the BRF3, T-shaped. But over here we have a bunch of lone pairs. But do you notice how the bonds are still 180 to each other? Because the lone pairs are pushing equally on all three angles, all three sides, I guess you could say, on this bond here, right? There's no imbalance, in other words. Okay, over here there's an imbalance. We have a lone pair on the left pushing these bonds towards the right. Here we have a lone pair towards us and to the left pushing these two bonds that are vertical a little bit closer together. But now we have here three lone pairs. It's all balanced, at least in the, well, it's balanced everywhere in the, what do you call it, the X direction and the Y direction as well. All right. Real quickly, okay, 4 members for the Trigonal Bipyramidal family. We're only going to look at 3 members of the octahedral family. Octahedral meaning 8, because it kind of looks like a square pyramid, 2 square pyramids fused together, but they call it octahedral because you have 8 faces. Okay, 4 on the top, 4 on the bottom. Octahedral, in this case, we're going to remove the first atom is the bottom atom. Okay, let me show you that. Okay. Here is octahedral. Okay, 6 balloons. 6 balloons. Now, if you have 6 balloons and only 5 atoms, because one of the atoms is replaced by a lone pair, remove the bottom one. And you have now what's called square pyramidal. If you have 6 balloons, and I'll put the balloon here. If you have 6 balloons, but only 4 atoms, 4 outer atoms, we got to remove this one here. And now we have what's called square planar. Definitely that top one would be the one to remove. Okay? Because now all the atoms, outer atoms, or all the bonds are separated by 90 degrees. Let me just double check something. Yeah, it would be you would remove the top atom to make it square planar. Okay. Let me show you that, and then we could be done with this video. 3 members only, and there they are. Square pyramidal, square planar. Again, they all have 6 balloons. It's just that the number of outer atoms changes. Now the bond angles here are 90 degrees. Okay, 90 degrees. Okay. What I suggest is you have all of these different examples. Okay. Why don't you can put these on a note card, or you could, I'm looking forward to full screen. Okay. Or you could put these on little post-it notes and then scramble them. Okay. And test yourself. What's PCl5? Okay. Without looking obviously at the chart. What would be the electron domain shape? What will be the molecular geometry? What would be the bond angles? And would the bond angles deviate from ideal? Okay. Okay. Have fun with that. Get very good at this because we do, in the next video, need to know these geometries because we're going to now look at some properties that are going to be very dependent on whether you have whether you have something like Trigonal Pyramidal versus Tetrahedral. Okay, they're in the same family, but they're going to have different properties, mainly due to this lone pair right here.